Hi, I'm Lisa Lippincott, and I'm here at home talking about neighborhoods banding together or reasoning globally about programs. Now, this is a bit of a departure for me. Usually, when I speak at conferences these days, I speak about reasoning locally about programs, but the usual warning still applies, which is that the code here is written in a fantasy C++ with a number of extensions that support local reasoning. I don't think they'll be too hard to understand, but they will be there and you can't expect to use them in your compilers today. Local reasoning is the process of looking at a program one neighborhood at a time and analyzing that neighborhood to see if the neighborhood fits the boundary conditions set by its interface and the interfaces that it connects to. So the fundamental idea of local reasoning is the neighborhood. And this is a schematic of a neighborhood in a program. The center of the neighborhood is the implementation of a function. So that's where things actually, well, kind of things actually happen. The neighborhood also includes, on the left, the interface to the function, through which it's entered, through which it's exited when the function returns. The interface can set up preconditions, it can set up post conditions in the epilogue, and it can relate conditions before the function to conditions after the function. The neighborhood also includes interfaces of functions called by the neighborhood. So anything that is called from the neighborhood, any interface that is called from the neighborhood is part of the neighborhood. But generally, the implementations of things that are outside the neighborhood are the implementation of the caller or the implementation of something called from the neighborhood is not part of the neighborhood. So this is enough to look at to see if the function meets its boundary conditions. I will say that I have found it's useful to include one more thing in the neighborhood, which is the bodies of inline functions that are called from the neighborhood. That's not shown here, but the bodies of inline functions that are called from the neighborhood are going to be, I'm going to consider part of the neighborhood unless that inline function is broken into an interface and an implementation. That's going to be important in about 30 minutes. So when you're looking locally at a neighborhood, you can think of the function fitting, the implementation fitting its boundary conditions as a sort of game. And in this game, there are two players, or perhaps it's better to say two teams of players. On the edges, we have the guys with the horns. The guys with the horns represent the forces outside the neighborhood that are causing the flow of control to enter the neighborhood. So the guys with the horns are responsible for making the preconditions of our function's interface hold as the implementation is entered. And they are responsible for making sure the epilogues, the post conditions of called functions hold. So the guys with the horns basically represent the outside of the neighborhood. The center of the neighborhood, though, the implementation, is the domain of the bald guys. So here we have a bald guy in charge of our function foo's implementation, but the bald guy is also in charge of getting flow out of the neighborhood. So every time an interface is called from the bald guy's domain, the prologue of that interface is part of the bald guy's domain. And anytime the function returns through the epilogue of that interface is part of the bald guy's domain. So we have this game, and what we do when we program is we try to rig the game so that the bald guy has a winning strategy and the guys with the horns always lose the game. And so local reasoning is basically about making sure that bald guys can win the local games in your programs. But we're not really interested in the big picture about whether individual functions in our program win their local games. We're interested in putting all the functions together. And when we put the functions together, we have places where there's a calling function and a called function. And each of those functions has its own bald guy. And we put the two functions together, making a combined game that we hope the team of bald guys can win. So when we link our program together, we're forming a bald guy team up that still needs to defeat the guys with the horns. And here, the game is different. The game is a combined game between the two, whereas each bald guy was playing their own individual game before. But the strategies are related because this is a game in which the bald guys are not playing a touchy-feely, everybody helps each other out sort of strategy. In this game, there's a plan, and every bald guy has a job to do, and every individual bald guy is doing his best to make sure that he is not the one who lets the team down by not doing his job. So in effect, each bald guy is playing a smaller game, the game of their job, and treating their teammates as if their teammates were guys with horns. So that's what happens when we link our program together. We form bigger games and we form bigger strategies by combining the existing strategies. Pardon me. So this is the framework for today's talk. There's local reasoning, and local reasoning is not our problem today. Local reasoning, any problem that can be solved locally, that can even be seen locally and understood locally, we're going to count as not today's problem. Today's problems, plural, are the ones that come from combining neighborhoods together, the problems that you can't see locally, that no individual bald guy can be held responsible for. And one example of such a problem is that sometimes you might have a caller and a called function that disagree on what the interface between the two functions is. These two might think the interface is different. They might be going according to different plans. And when you form the team up, what happens is they pull in different directions. They have different expectations of what's going on between them. And so you can end up with problems that neither in the interface that neither bald guy feels responsible for. And of course, that's going to make our teamwork fall to pieces. Now, this is a problem that shows up in a number of contexts in C++ and other computer languages. And C++ has a rule to deal with exactly this sort of situation. We have the one definition rule. The one definition rule is actually quite complicated because it spells things out in great detail, but the gist of it is here on the slide, which is there are many things in a program that must be defined, and those things fall into two classes. Some things may be defined only once in an entire program. So non-inline functions, .cpp sorts of things, all of those things are things that get defined once in an entire program. And then there's another class of things that can be defined repeatedly as long as you only define it once per translation unit. So inline functions are that sort of thing. .h file sorts of things. We put things in the .h file because we want the same definition to appear in many translation units, in many compilations. So each compile only sees one definition of those things, of anything. But when we link together, we are linking together compiles that saw different definitions. And when we do, when we have multiple definitions of the same thing, the rule says that all the definitions have to match. And it lays out exactly what matching means. Again, it's a long list of rules to get there, but the gist of it is that to match, two definitions have to use the same sequence of tokens. That's why using macros one of the reasons macros in your header file can really mess things up. It can cause you to unknowingly break the one definition rule where you thought you had satisfied it. And in general, the different definitions that come from different translation units have to refer to the same other entities. That is, the principal culprit here is overload resolution. If overload resolution went differently in two of the different definitions, then you could end up in two different translation units, then you could end up referring to different functions. You could end up calling different functions or taking the address of different functions where you should have referred to the same function. So to satisfy the one definition rule, generally, the definitions that are matching have to refer to the same other entities. There are some exceptions to that, and they are about situations where you can refer to different constant objects that happen to have the same value, because it turns out the value is the only important thing for making our program work. So that's the one definition rule. And since these interfaces and implementations are part of the fantasy extensions to the language, I'm going to extend the one definition rule to say that implementations of functions in general are .cp file stuff. They are things that may only be defined once in an entire program, with an exception for inline implementations. And I'm going to say that interfaces are .h file stuff. They may be defined once per translation unit. So we're going to see multiple definitions in different translation units, and when we link, we want them to match. And we want them to match according to exactly these rules, the rules of the one definition rule. Now, the one definition rule does spell things out in sufficient detail that we do know just what it means by definition. A definition is a mapping from a linkage name, from a unique identifier for the thing being defined, to a sequence of tokens, a bunch of values that that might be referred to, and linkage names of other entities that might be referred to. So the one definition rule tells us a definition looks like this. Linkage name maps to tokens and values in linkage names. And we can take advantage of that to find out if we have broken the one definition rule. Because when we're compiling, we could compile lists of all the definitions that we're using in a program. That is, each neighborhood could have, or each translation unit, which is a translation unit is now a union of neighborhoods, because each neighborhood does have a translation unit that contains the whole thing, that contains the whole neighborhood. So each translation unit or each neighborhood could have a list of all the definitions that it relies on. And if we want to see if our program satisfies the one definition rule, well, we sort unique, find adjacent, and we find any places where the same linkage name refers to two different definitions. So in this sense, in the technical sense, the one definition rule is entirely diagnosable. We don't require diagnosis of the one definition rule in the C++ standard. There are reasons we don't, but those reasons are not technical reasons about C++ so much as reasons about getting along with everybody who's using the linker. It turns out it's really hard to require things to be done at link time from the point of view of the standards committee. And there isn't a lot of getting together and agreeing to improve the link process in this world. So I explain this not because it's difficult, it's sort unique, find adjacent, it's standard library algorithms here. And I don't think it should be very surprising to any of you that sort unique, find adjacent finds duplicate definitions, or finds mismatching definitions rather. But this is an example of how we can check our global reasoning. And the example shows us the pattern. The way we can do global reasoning is we start with a local phase. We validate our small neighborhoods. We can use high complexity algorithms to validate small neighborhoods because the small neighborhoods are small and we can get away with applying high complexity algorithms to small data. And also in the local phase, in the compile time phase, we can describe the neighborhood interactions in a coarse manner using small tables. And then in the global phase, in the link time phase, we can collate the small tables into big tables, sort unique again, and then we can apply low complexity algorithms to the tables of interactions to find out if we have failed some global property that we want to maintain. So the global phase uses low complexity algorithms on big data. The local phase uses high complexity algorithms on small data. And this does require a little bit of making sure that your program fits the model. That is, if you make huge neighborhoods, you're going to create a problem for the model. If you create small neighborhoods that don't adequately express the global nature of their interactions, you could get a false positive in the global phase. So this is going to require occasionally some modification of the structure of program. Functions may have to be broken into two functions in some case. Sometimes different types will have to be used where one type sufficed before. But this is a scalable model of looking at global problems because we get to use high complexity algorithms locally on small data and low complexity algorithms on big data for the global phase, making the whole thing quite scalable. And this sort of thing does solve our one definition rule problem. It makes our function interfaces match exactly between the caller and the called function. But there's a hitch. There's always a hitch. Turns out there's a situation where you don't want the function interfaces to match exactly between the caller and the called function. Because a function interface tends to be very specific. A function interface expresses the interface to a function ideally in such detail that you would know why you would use this function rather than some other function. So here we have an interface for an identity function, and it specifies a property of the result of the identity function that very few other functions are going to have. So here, this function interface is very specific. And that's great if I'm calling the identity function directly. I get to know very much about what's going on inside. But if I'm writing an identity function, usually I'm using it in some context where I'm going to call it indirectly. And the indirect caller wants an interface that fits many different functions. So an example of that is an indirect caller that needs a non-decreasing function. So there are many different functions that are non-decreasing, but there are not very many functions that are identity functions. So this creates a problem. We have a caller's interface that does not exactly match our function's interface, but we want this call to go through. And we want to not break our global reasoning that says interfaces have to match between translation units. So let's fiddle with the language a little bit to give us a mechanism. And I'm going to call this mechanism interface adapters. It's an indirect caller's interface that, rather than thought of as fitting many functions, could perhaps be thought of as fitting many specific interfaces. So it's more general than the interface of the function that it connects to. And I'm going to say this works like a template in that you use non-decreasing here, this interface adapter, you use it like a template, you instantiate it by slapping it onto the front of existing functions. So in this case, we could have your non-decreasing interface adapter and identity, the function interface, the function that we want to connect to. And we're going to create a new function through a mechanism like template instantiation that has both interfaces in it, one on top of the other. So when you call this, the prologue of non-decreasing can execute, the prologue of identity can execute, the implementation of identity, of course, executes, the epilogue of the identity function can execute, and the epilogue of non-decreasing can execute. And so all of the conditions that functions are relying on can be tested in this path. And the reason to do this in a template instantiation sort of way, rather than some sort of conversion that replaces the interface, is that when we instantiate the template, we create a new neighborhood of reasoning. So here we have the adapter instantiation neighborhood, which connects the two interfaces together. So here we have bald guy with a monocle is in charge of making sure the adaptation came together right. And in his game, the outsiders, the guys with the horns, are playing the prologue of non-decreasing and the epilogue of identity. Whereas it's the monocle guy's job to make sure that the prologue of identity and the epilogue of non-decreasing will be executed without any problems. So here we have a new player in our game. The monocle guy is instantiated by whoever whoever attaches this adapter to this function. And so the monocle guy, again, his neighborhood exists in some translation unit and can be checked at compile time. And at link time, we now have the caller talking to the instantiation neighborhood, which in turn talks to the called neighborhood. And we make a three-way bald guy team up. So the sunglasses guy, the caller, sees the interface of non-decreasing. He sees the interface that he shares with monocle guy. And the interface is on the nose. It has the same stream of tokens. It refers to the same values. It refers to the same other linkage names. It's one definition rule exact match. And on the right-hand side of the diagram, the monocle guy connects directly to the guy with the hat, and they match on the nose in the interface of the called function, the detailed function interface, the interface of identity. So that's our solution for situations where we think there's not quite supposed to be a match. We invent a new neighborhood that fits in between. Again, changing our code a little bit perhaps, but we create a new neighborhood, in fact, changing our language a little bit to do this. We create a new neighborhood that make the matches on the nose. Now, there is a little detail to this solution, which is that we do need three kinds of function adapters, because we have three kinds of indirect calls, all with slightly different syntax in C++. So we have indirect calls through pointers and references to functions, the ordinary indirection. We also have indirect calls through virtual dispatch. And we have indirect calls through pointers to member functions. And they all work just a little differently from each other. So we need interfaces, we need function adapters that work just a little differently from each other for these three cases. I will point out that a pointer to member function can, of course, point to a virtual function. And when that happens, you're going to end up with a four-way bald guy team up. So this idea of functions as things that connect interfaces together also leads into another non-local problem we might have in our program, another problem that can't be seen by any individual bald guy. So if you think of a function neighborhood or an adapter neighborhood, any sort of neighborhood as connecting interfaces together, you can of course see that if you connect enough interfaces together, you may find that an interface ends up indirectly relying on itself. We could have a recursion. And this is a non-local recursion. This isn't viewable. It isn't possible to analyze an individual translation unit of the program to see if the functions in it are recursive. No individual bald guy can see that there's a cycle here. No bald guy can see the recursion. So of course, the recursion can't actually be the fault of any individual bald guy. It's a global problem. And the global problem gets a little more complicated by the fact that there are two kinds of recursion. There's unbounded recursion, which is the bad kind. Unbounded recursion might go on for a very long time and blow out our stack. And that would be bad. Bounded recursion, on the other hand, is a kind of recursion that most of us, at least, are willing to allow in our programs. So we need to make a distinction between unbounded recursion, which we want to get rid of using some global reasoning algorithm, and bounded recursion that we want to allow, that we want to not complain about when it's in our program. So the difference between unbounded recursion and bounded recursion is, of course, a recursion bound. And the recursion bound, here represented by distance from the center of these spirals, is something that decreases somewhere in every cycle. It has to decrease as you go round and round your spiral. It also has to never increase, because you could wipe out all of the progress you've made by decreasing by increasing it in some other part of the spiral. And the final thing that a recursion bound needs is to eventually run out, a mathematical property called well-foundedness. But eventually run out is really a good way to think about it. So we want to avoid recursion bounds that involve things like fractions, which might not eventually run out, or negative numbers, which you can keep decreasing without ever running out. We want somewhere in our program to be a check that our recursion bounds, the ones we are actually using, will run out. We could, of course, use fractions as long as we used them in some way that would eventually run out. So this, again, telling if something is a good recursion bound is a non-local problem. You can tell because two of the rules talk about something that happens with respect to cycles, and cycles are non-local in a non-local recursion. No individual bald guy can see a whole cycle. But there is an aspect of those two rules that we can see locally. And in fact, I've color-coded things in this picture to show it. We can see locally that certain steps, certain bald guys making a connection from one interface to another will always decrease the recursion bound, because that's That's a local problem. It is within the domain of one bald guy. There are also steps that might increase a recursion bound. And again, that's a local problem. Seeing whether the step increases the recursion bound is something that is in the domain of one step, of one bald guy connecting one interface to another. So I'm going to use these two symbols, the green check mark and the red do not cycle sign, to indicate these two kinds of steps, steps that locally are shown to always decrease the recursion bound, get the green check mark because every cycle needs one, and steps that might increase the recursion bound get the red mark because they are not allowed in cycles. And using these two marks, we can put together our strategy for global reasoning. So here we have, in our local phase, we will set the problem of making sure the recursion bound eventually runs out. We'll set that as a local problem. We'll get back to that. But in our local phase, we will also compile lists of the steps that connect interfaces. That is, each neighborhood, as we compile it, we will say it makes connections between its interface and these other interfaces. And we will mark the ones that possibly increase the recursion bound with the red mark. We will mark the ones that necessarily decrease the recursion bound with the green mark. And again, local phase, not really our problem today. Today we're here to talk about the global phase, where we check that no cycle contains a step with the red mark. And we check that, I'm getting some questions. I'm going to take questions at the end, thank you. So we check that every cycle contains a step marked with the green mark. So at the end of our local phase, we have a list like this. Or a number of lists like this. Individual neighborhoods compile lists of what interfaces they see connecting to what other interfaces. And these connections can take a number of different forms. In direct function calls, we are connecting something to a function interface, and the caller may have its own interface, or it might be called from inside an interface, or it might be called from inside an adapter. Indirect function calls connect things to adapters, as we saw before, and the adapter implementation point can connects an adapter to an interface, or in some cases when we're forming the big bald guy team ups, we connect an adapter to another adapter. So all of those count as arrows to put in our tables of arrows over here. And so these are the connections. We've marked some of them with red and green marks. And then we can go to our global phase. And in the global phase, as usual, sort unique starts our global phase. And we have a big table of arrows. And what do you do with a big table of arrows? Well, you make a graph. I'm going to start by making a forest. What I'm going to do is build a forest, top to bottom, depth first, left to right. And I'm going to throw arrows into the forest as long as they don't break the forest property. And so not breaking the forest property means I have to skip arrows that go back to someplace I've already been. So that's how I have built this forest, which has just one tree in it. The arrows that go to places I've already been come in three kinds. One kind is a downward arrow. It runs parallel to some path in the forest. There are also the opposite upward arrows that run anti-parallel to some path in the forest. And I'm going to include simple loops as upward arrows. So simple loops and things that run anti-parallel to a path in the forest are upward arrows. And the remaining arrows are leftward. That is, they connect one tree to another tree in the forest, or they connect one branch of a tree to another branch of the same tree, but they always go to the left because they go to some place we had already been when we got to their tail, and that means to the left. So now that we've categorized these three kinds of arrows, we can treat them individually. Upward arrows always add a cycle to our forest as we put them in. So we'll go through the upward arrows and mark the upward arrows and the arrows of the forest that they are anti-parallel to with cycle marks. These are parts of a recursion. Then we'll come to the leftward arrows, and we'll take each leftward arrow and see it doesn't create a cycle on its own, but it can extend some existing cycle. So if a leftward arrow forms a triangle by remaining inside a single tree, and the left side of that triangle already has a cycle mark, then we will put cycle marks on the right side of the triangle and on the leftward arrow. Now this rule can chain. So we have to apply it left to right because it chains left to right. We can apply it in one pass as long as we apply it left to right. And finally, we look at the downward arrows, and the downward arrows participate in a cycle only if the arrows they run of the tree that they run parallel to all participate in a cycle. So rule 1, rule 2, rule 3, apply those in order, apply rule 2 left to right, and we have identified all the cycle marks, all the arrows that participate in recursion in our graph. And having done that, we can compare it back to our list, find the arrows that have cycle marks, but also can increase the recursion bound. So here, that downward arrow that can increase the recursion bound is a problem because it's part of a cycle. The other arrows with red marks are not part of a problem. They increase the recursion bound, but what they're doing is setting up a recursion bound for the recursive part of the program to decrease. So that's fine. Increasing the recursion bound is fine and in fact expected when you're setting up a recursion. But during a recursion, you want to keep it going downward. So that enforces our red rule. We find all the cycles. Maybe you have been through a graph theory course and you know a better way to find cycles. It's not hard to find cycles. But this algorithm finds our cycles, finds and can compare them against the places that may increase the recursion bound. The green rule is pretty similar, but we start with checking the green rule by throwing all that work away so that we're back to just our list. Then we strike the green arrows off of the list and we build a new forest just like before. Now, this one looks very much like before because I cheated and picked an example that didn't involve drawing a lot of new stuff. In general, your forest may look rather different. But in my example, it looks pretty much the same. Once we have drawn the forest, we run through rule 1, rule 2, and rule 3, and we find any cycles that are left. Those are cycles that have nothing marked with the green mark. That's a bad cycle that does not decrease the recursion bound. It can be unbounded because the recursion bound doesn't decrease during the cycle. So that's how we do the global reasoning part of this. It's simple graph algorithms, soup to nuts. The whole thing is n log n. So low complexity, we can apply it to big data. But you may be a little disappointed that I didn't talk about really what a recursion bound is. That is, I talked about how it has to work mathematically. It had those 3 rules, but I didn't tell you how to spot it in code, how our neighborhoods agree on what the recursion bounds are and whether they're increasing or possibly increasing or necessarily decreasing. So I will get into the local thing a little bit. So here is an example of a recursive function, count recursively, which counts a sequence in pretty much one of the worst ways imaginable. But it is a nice example of recursion because it counts its tail recursively. Now, the recursion bound needs to be specified in the interface of a function because the interfaces are where the different neighborhoods are going to find agreement. So let's add an interface to count recursively. Here, again, I've just sort of shoved it off on some other piece of text because pretty obviously, my recursion bound needs to be specified by this thing recursively reachable that is being asserted in the prologue to this function. It's recursively reachable is something that is a precondition for the function. And somehow this precondition has to express what the recursion bound is. And this part, fairly straightforward, but and you could plug in more or less anything here that has the right properties. But I do have a favorite thing to plug in here. So I'm going to show you my favorite way to express a recursion bound. And I kind of hope that if this ever gets deployed out to real languages, this is how recursion bounds are going to be expressed. Here we have a claimable function. It's a thing you can assert. And when you assert a claimable function, you're asserting that the execution of this function will succeed and return to its caller. And this particular claimable function is recursively entailing itself. That is, recursively reachable is itself a recursive function. So it sounds like I'm cheating, but I have added the word inline to this function. Inline functions, as I said about 30 minutes ago, I'm going to consider part of the neighborhood that is calling them. So recursively reach, all of the iterations down recursively reachable are local to any function that calls count recursively. It sees the whole recursion in its neighborhood. And so any function that calls count recursively has to get through the prologue and has to find a path that makes recursively reachable return just in order to get to the implementation of count recursively. So in doing so, the calling function is showing that the recursion eventually runs out. Property 3 of recursion bounds, they eventually run out. So this is just loading a whole recursion into a single neighborhood so that it can be looked at by local reasoning, which is not our problem today. The actual mechanism of looking at that is fairly ordinary for local reasoning because it's just matching branches against branches to see if the recursion is going to terminate. And local reasoning is all about being able to tell that certain branches will go the same direction as certain other branches. So when we look at this from the caller's point of view, in order to assert recursively reachable, the caller has to provide the spiral that makes recursively reachable end. So and there's just this list of this called this, called this, called this, that the caller has to see before it can get to, before the test of can succeed, or before local, or it has to show that it exists in order to form a proof that this local recursion is going to end. Now, of course, one of the callers of count recursively, one of the callers of count recursively is count recursively itself. Count recursively has to show a spiral every time it calls itself. And what count recursively is going to do is take the spiral it was given, and when it calls itself, it will show a subspiral of the spiral it was given. So it keeps showing smaller and smaller spirals, and we know they're smaller because they were actually nested within the spiral in its interface. They are matched branch for branch identical because it's doing the same thing that was in its interface. Everything is substitutable. So count recursively it takes the spiral at its interface and calls itself with a piece of that spiral. That's decreasing the recursion bound. Increasing the recursion bound would be creating some new spiral that can't be matched branch for branch with something in the spirals you were given in your prologue. So possibly a piece of it could be, I might make a bigger spiral, that would be increasing. I might create a new spiral, that would be increasing. But if I take a piece, but not all of the spirals I was given and pass them to another function, that's decreasing. If I take every spiral that I was given in full and pass them to another function, that's neither increasing nor decreasing. Now, the reason I think this is a great way to represent recursion bounds is that it's effectively building a model of the recursion you intend to make. So, in order to call count recursively at all, I have to build a model of the recursion in count recursively. And each time we go around the cycle, each time we call some further function in the cycle, we pass the model, and at certain points in the cycle, we cut off part of the model and pass a smaller piece of the model. And eventually, because the model had to run out, because this was actually a test that was done in the neighborhood that originally entered count recursively, we know that eventually, as we keep decreasing the size of this model, we run out of pieces. And that idea can be fit neatly into a number of other sorts of interfaces. You can fit it to the particular recursion you need. If you need a tree-shaped recursion, you can write a tree-shaped recursion bound. And if you need I think something may have gone wrong with my slides. There we go. Here, I will show the tree-shaped recursion bound again. If you need a tree-shaped recursion, you can have a tree-shaped recursion bound. If you want a two-phase recursion, you can have a two-phase recursion bound by having two inline claimable functions, each entailing the other. So this sort of thing lets me create a model that matches the problem at hand. And that's actually, on a much larger scale, almost a theme in my intellectual life, which is this: represent like with like. If you are given a choice between two representations of the same thing, one of which has a lot of linguistic noise, a lot of linguistic distance between it and the thing you want to represent, and the other is very like the thing you want to represent. If you want to be clear, if you want to be clear in your thinking, if you want to be clear in your explanations, you do well to represent like with like. Now, the Latin, while it lacks a certain clarity, does make up for that in obscurity. And if you want an enigmatic way to end your novel, sure, go with the Latin. But if you want to think clearly, if you want to explain clearly, represent like with like. And on that note, thank you for listening. Are there any questions? I'll be looking at the chat. Somebody asked, since memory addresses are just 64-bit integers, wouldn't that mean technically any pointer is reachable from any other pointer? Okay, there are two different ideas of reachable in play for, they're similar here. And in general, I would say no. But actually the reasoning is the same for both. Yes, if you look at the implementation eventually on many implementations, but not all, that loop will terminate in some way, but it will have invoked, or that recursion would terminate in some way, but it would have A, taken a very long time, so you would notice it in testing, and B, it would invoke undefined behavior long before it got to actually repeating or actually terminating. And that undefined behavior would be a local undefined behavior, which again is a problem of the local reasoning, which you can see my other talks for more about the local reasoning. I will say that that the undefined behavior there is actually because pointers are not really unsigned integers. They are represented in a similar way to unsigned integers, and they are so close that it's easy to conflate them in our heads. And in fact, the computer underneath conflates them. But to the language, a pointer and an integer are very different things, and they work by different rules. Next thing. Do I think that global reasoning is in the domain of static analyzers or possibly residing in the compiler/linker or both? So A, yes, this is exactly in the domain or should be in the domain of static analyzers. A long-term, very deeply long-term goal of mine and many other people is to get us to the point where static analyzers actually show that our programs don't have undefined behavior, that they don't have unbounded recursions. And getting there is a long trek, but that's basically what all of my talks are about, is how do we get there? And of course, the global reasoning can't possibly reside purely in the compiler. You do need this link phase where you look at the big picture. But if the compilers prepare the right stuff for that phase, the big picture global checks can be done with efficient algorithms. Or at least I hope they all can. Next question. I think that this whole thing is describing a kind of whole program correctness algorithm. You think correctly. And the additional notation would really be a language addition to help that analysis. You also think correctly in that. So if I were king of C++ and I didn't care one whit about disrupting other people's programs and other people's development, then yes, these things would be going into C++ 20 right now. And I'd probably get them wrong because I would have done them all by myself without input from the hundreds of other people who work on making C++ a better language. So it's perhaps best that I'm not king or queen of C++. Let's see. What would be some resources or references for people who wanted to learn more about this field? Okay, there are lots of people around who can talk to this. You certainly have a whole bunch of talks by me on YouTube that you can listen. This is, in some sense, maybe the 6th talk I've given on different aspects of reasoning on programs. I particularly recommend last year's talk, The Truth of a Procedure, for a good overview. And one that I gave several years ago, which you'll see the notation is somewhat different in, is what is the basic interface? That was a fan favorite. Okay, next question. Does reachable recursively still reduce to the halting problem at the local level? Is the assertion that you don't blow out the stack at the local level that you can't move to the global? Okay. Another talk that I will recommend, a couple of years ago, I gave a lightning talk at Meeting C++ called The Halting Problem is Not Our Problem. And in synopsis, the halting problem, when you look at the whole problem, is the problem of whether or not a program that you found in the gutter, that you found carved into hieroglyphics by aliens in a pyramid, is going to halt. You don't find programs in practice in the gutter or in ancient pyramids. Programs are actually artifacts of human intention. And the halting problem doesn't describe the process of having the person who understood why the program was supposed to halt write down those reasons so that other people could check them. And so the halting problem is an analog of Gödel's incompleteness theorems. The checking proofs, doing automated code review with a sufficiently advanced language can be an analog of Gödel's completeness theorems. And that's an entirely solvable problem. So automated code review is something we can do. And so we might say, here is a program, we don't know whether it halts, but we do know that it doesn't say why it halts. And if we see a program that does say why it's halt and the reasons make sense, we're not up against the halting problem. We know because the reasons make sense. It does halt. Next question. Let's see, what other, we have time, I guess, for one more question. So what other properties of local or global reasoning that I still have to explore? So I will say, when I started preparing this talk, I was preparing a very different talk about how the reasoning around using global variables safely works. And all of this turned out to be material that had to go in the introduction of that talk. So one day, I hope, I will talk about global variables. So there are a great many problems already explored in my other talks. Another one that I'm hoping to do sometime soon is how different neighborhoods can make promises to each other that go beyond what's in the interface of adjacent neighborhoods. And there's one that I think I attempted to cover many years ago, but I really want to do a better job of. I have in the back of my mind a talk on why loops end that one day, hopefully, I will get around to putting together. Let's see, I guess I have one more question here. I'll let my team on the other side tell me when I have to stop. So are there any examples of languages besides C++ that have achieved this kind of static analysis? So many have attempted it, none have completely succeeded. So I understand that Ada has quite a lot of work going into this. I will say that there's the place I got started from was many years ago. There's a book, The Science of Programming by David Griese or Griese, I don't know how to pronounce his name, that was really an attempt to do this same thing. And in some sense, what I do could be considered reply to him. So many people are working on it. Many have invented new languages to try and do this. And some are working with existing languages. I prefer working with existing languages because working with an existing language keeps me honest. I have to actually do the weird details that come from a language that is used for a huge number of programs. Okay, apparently that is it. I will say one more thing, which is in a few minutes, I'm going to be going to floor 5 of the hallway. So if you want to buttonhole me, go to floor 5 of the hallway. Thank you very much.